So basically, this is where we stopped yesterday. We're studying ULXs, for those who forgot, and we want to know the mass of these objects, and we want to know why they are a factor of 50 brighter than galactic X-ray binaries or black holes. And we can use 3 different tricks. We can use beaming, we can invoke higher black hole masses, or we can use super Eddington luminosity, or any combination of these 3 factors, as long as the product gives you a number of order 50 or 100. So there's virtually endless combinations of these 3 factors. And if you want to constrain them a bit more, then what you should do is try to find common features that seem to be recurrent throughout the ULX population, see if you can constrain these models. And this is what I'm going to do in this talk. And I'll start from what is possibly one of the most well-known common features. This is the so-called soft excess in the X-ray spectra. And if you are a little bit more adventurous, you can say that it is the signature of an accretion disk, and then you can go one step further and say that this could be evidence of higher black hole masses or intermediate mass black holes. Now, pretty sure that you all agree that we can take a typical spectrum of a bright ULX and fit it with the power law. Fits reasonably well here, and then you're left with the soft excess. This is exactly what we saw yesterday, referring to AGN, so we have a similar situation here. We got the soft excess that may be fitted with a thermal black body or disk black body component with this kind of temperature. This is fairly common among the brightest ULXs, although some of them have got a pure power law spectrum. This is work that Lisa Winter has been doing with Rich Muschotsky. So are they evidence of intermediate mass black holes? Well, no, the situation is not so simple, because the same spectra can be interpreted equally well in at least 2 alternative ways. This is exactly what we saw yesterday for AGN. We remember compound-Stoke and Andy-Fabian-Stoke. So we can say that soft excess is cool disk emission, or we can say that there is some kind of smeared absorption in an ionized outflow. This is the same spectrum I showed before. We can also fit it with the power law plus this kind of absorption trough. And you can simply do a power law minus disk black body fit, and you get a fit that is even better than the power law plus disk BB fit that we did before. Now, this absorption graph, of course, is not just put there ad hoc. It is exactly where you expect it to be from theoretical calculations. And this is work that Annabella Gonçalves has been doing. So you take an injection spectrum, you send it through an ionized outflow. Outflow is sufficiently fast that it will smear all these absorption lines. And so from the injection spectrum, then you take this large chunk out, and this happens to be exactly where you would find it in these ULXs. So we have at least 2 possibilities: cool disk emission or some kind of processes, absorption, re-emission, and reflection in this ionized outflow, plus any possible combination of the 2. There's no reason why it should be either or. We may be seeing a little bit of a disk component and also this effect in the wind. And even if you think that you can identify the disk emission, then you have at least 2 possibilities. You can say that it is a standard disk around an intermediate mass black hole, or it is a non-standard disk around a perhaps stellar mass black hole. So again, a lot of different alternative possibilities. And we can go on for the rest of the talk discussing the merit of each of these alternatives, but we would be missing the point. And the point is that these are first-order corrections to a spectrum that it is essentially a non-thermal, power law-like, if you like, spectrum. So that's the main point that I want to convey at the beginning of this talk. Most of the emission comes from a non-thermal component, or a power law component, if you like. The disk is only radiating less than 20%, or maybe even less than 10%. Now, this suggests that most of the power is not radiated directly by the disk, but is efficiently transferred to another medium that can be a corona or a jet or an outflow or maybe the base of the jet, which is then producing the power law component. And also, as a consequence, if you accept the suggestion that most of the power is transferred from the disk to something else, then it implies that the disk may be cooler than a standard disk that radiates all the gravitational power, simply because most of the power is in fact taken out of the disk. The disk is drained of gravitational power, so it may be cooler than a standard disk for the same size and same black hole mass. And this is just a cartoon. Zdenka Kuncic will get into more details. What I'm saying is that instead of having temperatures rising like in the standard Shakura-Sunyaev disk, you have a temperature that flattens out because most of the power here is not radiated by the disk. And if you do, instead of using the standard Shakura-Sunyaev scaling relations between temperature, luminosity, and mass, if you take that into account and redo the same back-of-the-envelope calculations, you get masses that are not between 500 and 1,000, but are in fact much lower. They're order 50. And the crucial factor is how strong the power law is compared to the disk B component. So that's a way to reconcile these objects, these X-ray spectra, with stellar mass objects. And we also get accretion rates that are, for the same reason, that are above Eddington. Now, this was just one common feature of some of the brightest ULXs. Now, we'll quickly go through other features that may help us understand the nature of these sources. Another possible feature is the presence of jets. Now, we do not see direct evidence for jets. We don't see like core emission. We do see expanding synchrotron, optically thin synchrotron bubbles that are most likely radiolobes. They seem to be too bright to be, too energetic to be normal supernovae, and also too large to be young supernova remnants. This is just one example of a ULX detected in the radio with an optically thin synchrotron bubble. This is just a starburst region, but so it's got a flatter spectrum, and this is the ULX. And also, another indirect evidence of outflows would be optical nebulae, the kind of nebulae that Manfred Pacu's group have been studying. That's in 1313, and that's a source that we heard about yesterday. Some people might even see 3 rings here, if you've been to... but yeah, that's, could be taken as evidence of outflows and hotspots. So, outflows and jets, conclusion, they may be an essential ingredient. We expect them to be, but we need more evidence. This is an essential ingredient, young host environment, especially for the brightest ULXs. They all seem to be surrounded by relatively young stars, or to be in star-forming galaxies. Elliptical galaxies don't have very bright ULXs. And young means less than 50 million years, which means likely to be an OB star, or at least consistent with an OB donor star. We can go even further and say, what about starburst? Not just star formation, but starburst. There is some association, because some starburst galaxies have got a lot of ULXs, but this is not a necessary ingredient. We do have tidal dwarfs with very little star formation and bright ULXs. What about superstar clusters? No, that is not an essential ingredient. We see a ULX associated with the superstar cluster, and that's about it. Maybe one more, but most of them are not in superstar clusters. So obviously that is not an essential ingredient. Collisions. All sorts of types of collisions, galaxy collisions, cloud galaxy, cloud disk, and a lot of them are associated or near ULXs. So that seems to be a common thread of the bright ULX population, to be in colliding or tidally interacting systems. Important ingredient. That's just some examples. There's galaxy-galaxy collision in the antennae, dwarf galaxy on disk collision in this, and that's the ULX right here. Again, galaxy-galaxy collision. And mind you, the collision doesn't have to produce a starburst. I'm talking about the direct association between collision and ULXs. In this galaxy, star formation goes on in here, 10 solar masses a year. The ULX is here. There's very little star formation, but there's an H1 cloud sticking out right near the ULX. And if you do a velocity map, this cloud is actually hitting the disk at a speed of about 100 kilometers per second. And it seems to be merging or hitting the disk right where the ULX is located, which is just, it's interesting. You know, it's maybe something to follow up, to understand if it's just a coincidence or not, or if it is doing something, you know, some kind of star formation there. Low metallicity. Again, this seems to be an important ingredient. Most bright ULXs seem to be associated with low metallicity environments, and also theoretically we expect metal poor stars to leave behind more massive remnants. Now, having gone through all these possible ingredients, let's see if we can string them together and conclude something that makes sense and learn more about the nature of ULXs. And I will start from the nature itself. I would say that the simplest model, the most conservative one, the one that says that ULXs can be explained as the upper end of stellar mass objects, is still consistent with the data. I'm not saying that intermediate mass black holes are ruled out. I'm just saying that the most conservative hypothesis that they come from stellar processes is still consistent with the data, and for example with the X-ray spectra, even with the soft excess and the flux. Ages, we said young ages. If we say that they can be formed in stellar processes and they have masses around 50 or definitely less than 100, then we need a progenitor star that has to be at least 200 solar masses or around 200 solar masses. And you need low metal abundance to go from a very massive progenitor star to a black hole. This is not ruled out by current stellar evolution models. We know very little about the evolution of a 200 solar mass star, let alone the evolution of a metal-poor 200 solar mass star. And how do you form a very massive star? Well, you don't form them in normal Jeans mass fragmentation of a molecular cloud. The only way to form such massive stars is when you have trigger star formation of a molecular clump that is not fragmenting, it's collapsing on itself. So you have dynamical collapse of a molecular clump, and that will produce a protocluster with very massive stars in the center. And we may just speculate that if we have trigger star formation, triggered, for example, by pressure waves from collisions, you may end up forming more massive stars. And then, if you have metal-poor environments, you may end up forming a rather massive stellar, so to speak, black hole. So this is just a way to try and understand why low metal abundance and cloud galaxy collisions seem to be associated with ULXs. It's just a speculation. But mind you, each of these steps is well known and studied, even in our own galaxy. I'm not just making it up. The thing is, I'm just suggesting that if we can string them together, then we may end up with the production of a massive remnant. For example, this is an example in our own galaxy of a molecular clump in here, which is dynamically collapsing rather than fragmenting. If you've been to the symposium on trigger star formation last week, you would have heard everything about this. It's collapsing. You have an inflow of a few hundred solar masses of gas onto a few already quite massive protostars, still surrounded by thick gas. And the idea is that they could likely merge into something bigger, something at least 100 solar masses or so, and still accrete maybe another 100 solar masses of gas in the center of this collapsing molecular cloud. Except that this is in our own galaxy. It's in the Cone Nebula. If there are any amateur astronomers, they would have recognized it. I had no clue what it was, but yeah, I'm told it's a Cone nebula. And the thing is that this is too matter-rich to form a massive black hole. But the process of star formation is happening. And you do form very massive stars, like the Pistol star, 200 solar masses, or there's one in the LMC, which could also be around 200 solar masses. Just the trick is to make sure you get a black hole out of it. Now, final slide, conclusions. Power budget. If we think that they are around 50 solar masses, then we need accretion rates or 10 times Eddington. Luminosity will be a few times Eddington. Something I said before, I want to stress it again. The disk is only radiating a small fraction of the gravitational power, which means that the rest is still available to be taken out and used for outflows or jets. And the disk may be cooler than standard models. If this is the case, super Eddington accretion, lots of power available for jets, then we can have an interesting situation with a probing regime of outflows and jets in black holes accreting above Eddington. Now, we know that there is a similarity between low mass X-ray binaries and low luminosity AGN at accretion rates much below Eddington. This could be a local equivalent of high redshift quasars accreting well above Eddington. So we can use ULXs to study that regime that was typical of those early black holes when they're still growing at an accretion rate much above Eddington. We want to see if it was effectively above Eddington mass accretion with low relative efficiency, or highly efficient accretion accompanied by outflows and feedback. So we've got lots of things to study, not just to understand the nature of ULXs, but also to understand how they relate to black hole accretion in general. And I'll stop here. Thanks.
No question, please. Yes?
Roberto, you stressed the point that in most of the bright ULX, the power law component comprises maybe 80 to 90% of the flux. Mm-hmm. But I would assume that this depends quite sensitively on the way you feed the spectra. For example, assuming that you see a soft excess rather than absorption can change this statement. Am I wrong in this? Or?
The soft excess is in fact only a small component in the X-ray spectrum. If you feed the X-ray spectrum from 0.3 to 12 kV in the standard band, the soft excess will only give you a correction. It will not be dominant. So in that band, even if you extrapolate the soft excess at 0.15 kV, you extrapolate and you integrate of the whole DISP-BB spectrum, it will still be much less than the flux that comes out in the power law component.
Okay, yes, please.
Yeah, just a comment really, Roberto. The conditions you described for forming the ULXs sound very similar to what we see for the high redshift gamma ray bursts, and I'm just wondering if there's some common physics or common evolution here.
Yeah, I think yes, it's a good point, Elaine. I think it's related, something to do with very massive stars, but I'm not quite sure if we know more about ULXs. Like we can use ULXs to understand high redshift gamma ray bursts, or vice versa. We should move.
Okay, no more questions. So please run to the microphone.
Hello, I'm here.
Okay.
Okay. You have to be very careful with your estimation of the initial mass in a metal pore environment. In order to produce a 100 solar mass black hole, you quoted 200 solar masses. However, a 200 solar mass star in a low metallicity environment produces an electron pair supernovae. Actually, nothing is left. It certainly doesn't produce a 100 solar mass black hole. We have in Brussels, and I understand that Lev Jungelson also succeeded in order to evolve a 1,000 solar mass star, but with realistic stellar wind mass loss rate. And actually, they still these kind of stars that may produce 100 solar mass black holes?
It's a good, Danny, it's a good point. This is still controversial, but for example, if you look at calculation by Hager et al., they have a regime with metal abundance lower than about, say, 1/10 or 1/20 solar, in which there is a range of stellar masses that produce pair instability supernovae. But then once you go around SMC-type metallicities, I'm not talking about primordial, I'm talking about SMC-type, then the pair instability range kind of disappears in their calculations. So maybe at SMC-type metallicities, you do not have this pair instability gap. You may have just direct collapse. But I know very little about this, so I don't really want to say anything more.
Okay, so let's thank Roberto.